Hello. Thank you for your talk. I have a question. In one of your first slides, you showed that you were recording the vorticity. And do you have insight of what's happening in the intermediate region where the amplitudes are not so different? It seems that you have the mode 2 consists in two vortices, which seem to be splitted after collision. Does that make sense? Or?
Yeah, it does. You're entirely correct. So what we found was exactly as you say. So on the ones where it's deformed, you will have seen, you have these two counter-rotating vortices going along, and then when they feel the shear, they kind of get pulled apart, and they feel that for a certain amount of time, and then when the shear's gone, they kind of, they've essentially been pulled apart. And I think we saw that in the second example I showed you in the videos.
Okay.
What we don't have, unfortunately, from those experiments is really good PIV data because the seed moves so poor. So while we can measure the velocity field there and return some vorticity measures, they're messy, they're very noisy.
Okay, thank you.
Hi. Thank you very much for your talk. And I had two quick questions. One, I want you to talk a little bit about the numerics, specifically in terms of how long a computational run would take. Let's say for that tripartite graph you showed before where you were looking at the tank and then you were looking at the velocity fields. When you run an experiment and you take that data and then do numerics on it to simulate, how long would a numerical simulation take, or was it dependent on whether or not you were working with a mode 1 or a mode 2 or a combination of both?
Yeah, okay, thank you for your question. So the two-dimensional numerical simulations to replicate the lab are really quick. Okay, so we feed the numerical scheme, the lab density profile, essentially we fit to that, and we set up the numerical domain to mimic the tank, and we've done this in various studies and we've had really good agreement between the two. So for something that's two-dimensional, mimicking the lab, relatively quick. So for example, overnight, if even that long, you could run it on a laptop even. It can be, maybe that's going too far. We can kind of do the post-processing quickly on a laptop, but running the actual computation is probably overnight, if that long. The 3D obviously takes longer. Could I give you an exact time? I would have to refer you to Mara, probably more like a week rather than overnight. So you're looking at probably two-dimensional simulations, typically overnight. A three-dimensional simulation, maybe a week.
That sounds about right. My last question, follow-up question, is just where are you going with the work from here?
Yeah, so again, thank you for that question. We have an math student actually who's just started his maths on this, so we're hoping to do some energetic studies with the numerics. So try and get some, obviously the numerics is a lot cleaner with the laboratory, so we'd like to look at the energetics and in particular what happens to the energy from that mode 2 wave. Can we get some kind of exchange? Is there a way of linking the energy of the mode 1 wave to the energy of the mode 2 wave and vice versa? And they're kind of initial ideas that we've had, looking at as well as investigating the three-dimensionality in more detail.
Thanks very much, Magda. Again, would you join me in thanking Magda for such a fascinating talk? And our next speaker is Justin Cole from the University of Colorado, who's going to be talking about transverse instability of Peregrine rogue waves.
Can you hear me? Perfect. Okay, before I begin, I'd just like to take a moment and thank the organizers for the opportunity to come and speak to you all today. Enjoyed the talk so far, and I look forward to the rest of the week. I'm going to share with you some results in collaboration with Mark Oblowitz at CU Boulder, where I had done my postdoc before going down to the Springs, on the instability of the Peregrine rogue wave model. So what I'll talk to you about today, first I'm going to motivate a little bit about motivation for rogue waves. Since this is a diverse crowd here, I'll spend a little bit of time talking about our governing equations, deriving the nonlinear Schrodinger equation, and then I'll talk about the various instabilities that can occur. So, there we go. Okay, so I'll start with well-known picture on the left, the great wave off Kanagawa, Hokusai. Appears to be a depiction of a rogue wave event. Large, fearsome wave out in the ocean. People in the boat are in trouble. On the right are some photos taken from a ship that appear to be depicting certainly large waves, perhaps rogue waves, coming towards the ships. So rogue waves have been the tales of fishermen for ages. Some definitions of these freak or extreme waves. One is that they are uncharacteristically large amplitude waves that appear and then disappear. So there's a notion of temporal localization. Another definition attributed to Haber is a rare outlier event relative to the population of events in that environment. These should be rare events, and while there are probabilistic descriptions of the rogue waves, I'll take a more physical description of them. Another definition is waves whose crest height, the peak to trough, relative to the significant wave height exceeding some ratio. Significant wave height, 4 times standard deviation of the mean heights, but intuitively a measure of the amplitude of the waves in the environment. A common ratio is 2 for this quantity here. One more description that appears in the literature for Karev and Pelanovsky is a deep trough before and after the largest crest. So one could trace the origins of the scientific study of rogue waves to the well-known Dropner wave off at the Dropner platform off the coast of Norway. Here's the well-known time series. You have the time and the surface elevation at the location of the measurement. And what you see is the rogue wave event there, right in the middle, whose crest to height to trough amplitude is 25.6 meters or 84 feet. More importantly is the ratio of the crest height to the significant wave height, h over hs, which is 2.13, and so it meets that criteria for the rogue wave. So I'd like to spend a little bit of time now, so having motivated the rogue waves a bit, let me spend a little bit of time talking about the derivation of our governing equations and where they come from. So I'm going to consider a system like this in a 3-dimensional space, x, y, the transverse dimensions, z, the vertical direction. I consider an interface wave between water and air, which in general depends on x, y, and t. And then to simplify the problem, starting from the Navier-Stokes equations, I'll make common water assumptions, namely constant density, irrotational flow, 0 viscosity, a gravitational force acting in the negative z direction, and lastly, a deep water assumption so that the wave does not feel the effects of the bottom. From the incompressible Euler equations, we make a common approximation known as the quasimonochromatic approximation. We introduce a slow set of variables, capital X, capital Y, capital T here, related to the original variables by some small parameter epsilon. Okay? Using this 2-scale approach and looking for modulated linear waves of this form right here, eta, specifically with the form I look for an envelope U, which depends on the slowly varying variables, which modulates the plane wave, which corresponds to the linear solution. And then to make sure that this is a real wave, I add its complex conjugate. In terms of the linear wave, it obeys this dispersion relation right here for deep water waves, square root of g times the magnitude of kappa. Kappa here is the wave number, and it's inversely proportional to the wavelength. Specifically, we'll be looking at the envelope U, which, after moving into a traveling frame of reference, yields the what I'll call the 2 + 1 nonlinear Schrodinger equation, 2 for the two spatial dimensions in x and y, 1 for the temporal variable. This is it in its non-dimensionalized form with some coefficients depending on the physical parameters. So this is a prototypical nonlinear dispersive PDE. Many in this room have experience with this, whether it be water waves, electromagnetic waves, fiber optics, plasma, this goes on. So it's, I think, a fitting equation to study in this sort of a workshop on physical applications. Now, as I've non-dimensionalized it, there are a few parameters, S1 and S2, which will be plus or minus 1. If the sign in front of the y derivative there matches the x derivative, that's the elliptic case. If the signs disagree between the x and the y, that's what I'll refer to as the hyperbolic case. If the sign in front of the nonlinearity matches the sign in front of the x derivative, that's the self-focusing case. If they disagree, it's the self-defocusing case. Lastly, for a boundary value problem, let me prescribe some boundary conditions, namely u goes to 1 as x goes to plus or minus infinity, which corresponds to a traveling wave background. Now, what is the appropriate set of coefficients for the water waves? So I've taken this figure from the book of Abelowitz and Seeger. There's two parameters here. There's the depth parameter, kappa times h. Kappa, again, is our wave number. H is the depth of the water, which in the deep water, this is a large number. So kappa naught times h should be large. And then there's a surface tension parameter, T tilde there. So T tilde here is on the abscissa. The depth parameter is on the ordinate axis. And so if we're doing deep water, we want to be at the top of this phase diagram here. And for deep water waves, typically they are small surface tension. So we want to be in the top left corner, which is labeled as region D right there. You can ignore the other labels. We changed the notation here. Now, if one wants to stay in the deep water, but that's region D. And in terms of my equation in the previous slide, that corresponds to the hyperbolic focusing case. So S1 is -1, S2 is +1. If one stays in the deep water but increases the surface tension, the first region, region E right there, is the elliptic defocusing NLS equation. And if one stays in deep water but goes to the strong surface tension case, that is the elliptic focusing NLS case. The Dropner wave, which I mentioned earlier in my talk, falls just above, in region D, just above the line there in region A. So it's in this chart, it's in the deep water, but it's certainly on the lower end of that deep water regime. Yes? Kappa is the linear wave number of the linear wave we're modulating. Here, we'll go back. Kappa appears right there in the phase there. Okay, so let's start talking about rogue wave models. So I'll talk today about the Kuznetsov Ma and Peregrine solitons as models of rogue waves. So first, let's start with Kuznetsov Ma. Solution is shown there on the left. It's notable because it is localized in x, periodic in time. The peaks there have a peak amplitude. In this case, for these parameters, it's greater than 3. The peak in this case is local. One of the peaks occurs at the origin in the xt plane. The formula is given in this right here. Now, what's important here is embedded in these parameters, there is a z parameter, which for the Kuznetsov-Ma soliton is greater than 1. If one takes the limit as this parameter z goes to 1, then the time period of Kuznetsov-Ma goes to infinity, and you get the Peregrine soliton, which I've shown you in the top right figure there, its amplitude. The formula is down here. It's a rational solution. The peak amplitude of the Peregrine soliton is 3 on a background of 1, and it's localized in space and time, and it has a trough ahead and behind the peak of the crest right there. So it's an ideal description for the rogue waves using all of those criteria I mentioned at the beginning of my talk. Now, recently there has been some study of the stability of these Peregrine solitons in Kuznetsov mass. So here's a couple recent works. The first, there is a paper that came out in 2017 by Cuevas, Maravar, Kevrakidis, Frantzakakis, and others. And it's in spirit, it's similar to our work in the sense that it involves a Floquet analysis of the 1+1 Kuznetsov mass solitons. And the finding in that work was that they were unstable in the 1+1 problem. Some other works here, which include simulations of the 1+1 NLS equation. Klein, Haragas, Connie Schober, some of her works with Islas, Kalini, and Strawn, all show that the 1+1 case, small random perturbations can lead to significant instabilities. And also there is some, in the 2019 work, Kalini and Schober and Strawn, there's some IST calculations to back that up. So our question was very simple. The 1+1 stability problem of these Peregrine solitons had been studied already. What about the 2+1 case? Okay, if we're out in the middle of the ocean, there are two full transverse dimensions. What does the stability or instability profile of these solutions look like? So this is a question of transverse instability. So what we studied was, consider a line soliton there, U. It would be one of the solutions I mentioned, or perhaps even a plane wave solution. And consider a transverse perturbation of that solution. So I perturb U tilde by this specially chosen perturbation here, which is small in magnitude relative to the solution. Specifically, notice that my perturbation depends on the transverse direction y. The script L there is the transverse wave number. So doing the standard linearization procedure, I take this, I linearize about the solution, I get a linear set of equations which describe the evolution of the perturbation, W plus and W minus. They are parameterized in terms of L, the transverse wave number, and they notably have coefficients which are the original solution, U tilde. Okay? So there's two types of coefficients that we want to study. The first is the constant case. That is on the background of 1, the periodic traveling wave solution. And that's straightforward we can solve it, and I'll talk about that in a moment. That'll be the modulational instability. The second case, which we were most interested in, was the case of the Kuznetsov mass soliton, which was, recall, it was localized in X, periodic in time. So that's a natural Floquet problem, where you have a system whose, after discretizing in space, has coefficients which are periodic in the evolution variable. So I'll talk a little bit about that in a moment. Now, we studied the stability, just to kind of prepare you, of the Kuznetsov mass soliton so that we could use Floquet theory directly. And then our logic was, well, ultimately we were interested in the Peregrine soliton, but since the Kuznetsov mass soliton approaches the Peregrine soliton as that parameter z approaches 1, we conjectured that the stability of the Kuznetsov mass soliton also approaches that of Peregrine. So that was our direct way of, in terms of the linear stability of getting towards the stability of the Peregrine, and direct numerical simulations confirmed this to be a reasonable approach. So first, modulational instability. So this corresponds to solutions just that are 1, U tilde is equal to 1 here. Consider perturbations which include a modulation of the frequency. So there's a K up there that modulates the frequency of the wave number of the solutions. And as a result, there's also an associated correction to our dispersion relation, lambda here. Lambda satisfies, when one takes this and solves the linear stability equation of the previous slide, one obtains this algebraic equation right here. If the imaginary part, as I've chosen my form right there, if lambda has a non-zero imaginary part, then we have exponential growth in time. And if there is a non-zero imaginary part, then call that linear instability. We expect, even in the fully nonlinear problem, to see the effects of this. So what I'm showing you here on the bottom now is the magnitude of the imaginary part for two of the equations I mentioned to you earlier. On the left is the deep water strong surface tension case, the elliptic focusing NLS equation. Okay, what you see in the bright regions are regions of instability. The peak instability has a growth rate of 2, which is at the center of that donut region there. What you see is that there's no angular, the dependence is purely dependent on the radial distance from the origin. In terms of both the K and the L, which are the wave numbers of the perturbation in the direction of propagation and the transverse direction. Okay, on the right is the stability region for the hyperbolic focusing case. This is the deep water small surface tension case. Again, what you see is bright regions, the brightest region being a growth rate of 2, which is a hyperbola right in the middle of that bright region. This is bounded on the inside by 2 lines and on the left and the right by hyperbola. Notably, what you notice is a strong directionality here. Namely, if you look at the K equals to 0 line, the vertical line right in the middle, there is no instability predicted through the linear stability analysis. Okay. Now, okay, so that was the stability profile for the constant solution. Now let's move on to the Kuznetsov model, which is a class, as I mentioned, is a Floquet problem. So there's 2 pieces to this. The first is the monodromy matrix, which is the principal fundamental matrix solution, phi, after 1 period. So capital T would be the period of those peaks in the previous slides of the Kuznetsov model, parameterized in terms of the transverse wave number L. The principal fundamental matrix solution is the matrix solution with identity initial conditions. The second piece is we look for Floquet solutions using Floquet theory. Namely, the solution comes back to itself after 1 period up to a scalar factor rho, known as the Floquet multiplier. Combining these 2 descriptions of our solutions, what we have here is an eigenvalue problem. Namely, the Floquet multipliers are the eigenvalues of the monodromy matrix. So this is numerically how we get these, is we actually will explicitly compute the monodromy matrix and find its spectrum. Now, if we rewrite the Floquet multiplier rho in this complex form here, then what we see is that stable solutions correspond to Floquet multipliers on the unit circle in the complex plane, which correspond to lambda being real, if and only if. And it's easy to see why this is. If you take in forward forward evolutions of your solution, you're going to get rho to the power n. And if rho is off the unit circle, this thing is either exponentially growing or decaying. One more thing I'd like to mention that wasn't mentioned in the original paper was we're solving PDEs using in this approach here, and for rather dense grids, this can be a little computationally heavy. One thing we noticed that was very beneficial for speeding things up is to take advantage of parallelization. So you have a monodromy matrix, which is a fundamental matrix solution. Each column is a linearly independent solution of the equation, meaning they don't have to be solved in series. So you can get, through parallelization, you can get these running simultaneously, 32, 64 of the solutions being calculated in parallel. Okay, so that's the motivation. Let's look at some numerics. So what I'm going to show you is the imaginary part, the unstable parts of the Kuznetsov model solitons for different values of z. Again, as z approaches 1, the Kuznetsov model soliton approaches the Peregrine soliton. And so what I'm showing you here on the bottom now is the non-zero unstable part of the spectrum versus the transverse wave number L. The blue curves are projections of the modulational unstable curves I showed you in the previous slide, those hyperbolic regions there. That's the blue. It's bounded by 2. The red curves are what we numerically computed. Those are the 2 largest unstable modes for the Kuznetsov model soliton. What you see is that they overlap with the modulational unstable modes for large L values for all 3 cases. And then as z approaches 1, the Kuznetsov model solutions, and we would expect the Peregrine stability profile, goes to 2. It's just overlapping there at the very top of the unstable, the modulational unstable profile there. So what this suggested to us is that the Peregrine stability profile resembles that of the background modulational instability profile. We also did this for the focusing elliptic case. Again, the blue regions there are those projections of that donut region I showed you before. And again, as z approaches 1, we find that the unstable modes for the Transverse of MA solutions are approaching that of the modulationally unstable modes from the background. So to test this conjecture, we then went to numerics. So what we have here, let's start in the top left here. So I have a line soliton solution in the hyperbolic NLS equation. In this case, this corresponds to the z equals 1.25 Transverse of MA soliton. And then I've added a small perturbation. So the perturbation is localized in space, but it's also localized in the frequency domain. In the bottom right-hand picture here, I have a circle, and I have excited modes inside this circular region right here. And there's a little hard maybe perhaps to see, but there's a little spot there, and it's random inside that spot there. Okay, so it's a small perturbation, it's only 10%, and then I evolve it. So go from the top to the bottom, and what you see is that when the soliton is supposed to peak at time t equals to 0, there's been a complete fracture of the line soliton with this X pattern right here. In the top right figure right there, I'm showing you a side profile, but this is no longer localized in space. It has disintegrated, the solution here, due to this relatively weak perturbation. So to test the previous conjecture, does this fall over to Peregrine? The answer is yes. If you compare this slide to the previous slide, you don't see much of a difference. It's the same perturbation. The only difference is now this is the Peregrine soliton, but it's perturbed like before, and again, at the time of the peak, there's been a fracture of the line soliton. But one more thing. So we said there was the conjecture that the Peregrine stability should perhaps be identical or similar to the modulationally unstable profile. And I pointed this out to you before, that if you look at the modulationally unstable profile, along this vertical line right here that doesn't show up so well, but this is a vertical line centered at k equals to 0, there are no unstable modes predicted. Meaning, if what this corresponds to are perturbations which are random in y but constant in x. So if you see the initial condition with that sort of a perturbation, so up there it has y dependence, but it's constant in x, no instability development. This is a top view at the bottom left here. You can't see much. On the side profile, you can still see the few wiggles that were there because we started with it, but there's no growth here. So what we take this is that strong evidence that the stability profile of the Peregrine soliton, rogue wave, is that of the background modulational instability. If you do something, if you perturb this way, namely exciting modes in the x direction there, but not in the y direction, you get an initial profile that has x dependence but no y dependence, and you see a significant instability developing there. This would be the analog of what was done in the 1+1 case, those sort of perturbations. And to further support that argument that this is modulational instability that we're seeing in direct numerical simulations, I just took a constant background, a background of 1, took those same initial conditions I showed you before, and if you look at the bottom left, that's that X figure that was seen in the previous slide develop. If you look in the bottom right corner, you can see the instability that developed in the previous slide, the bottom left one down there. And in the middle one, if you perturb something that depends on y but not on x, if you look at the color bar, you see that nothing has grown. This is a 10% 0.1 perturbation. Nothing has grown significantly, appreciably. And so that's the hyperbolic case. If one goes back to the elliptic NLS case, so it's well known that the elliptic NLS equation in 2 dimensions has collapsed in finite time. So these perturbations, that's what we notice there, is as long as we could run it, there is a collapsing filament there whose width is going to 0, but its amplitude is going to infinity. So the numerics certainly show that. There. So I think I will wrap up here. So in conclusion, we studied the stability of a couple of rogue wave models, the Kuznetsov of MA and the Peregrine solitons. We found that both are linearly unstable in the hyperbolic as well as the elliptic NLS equations. They are found to be unstable at both small and large wave numbers, all different wave numbers. And the evidence suggests that the Peregrine instability resembles that, appears to be the same as that as modulational instability. And lastly, perhaps a better name for the Peregrine instability should be not transversely but obliquely, because the perturbation has to have some sort of a perturbation in the direction of propagation. So in hindsight, maybe that would have been a better description of the sort of instability here. There's the paper if one wants to see more details. Thank you for your attention.
Thank you. Can I clarify for myself the logic of instability analysis? Because Peregrine is localized in time. So it lives short, maybe bright life, but short. So it will die anyway. So of course, you probably can help it to die early by certain sort of perturbation. But I think role of Peregrine in this rogue wave interpretation is that there are some conditions then Peregrine soliton can appear from nowhere, they say. So, and in this sense, well, at least me, I don't understand instability analysis, because if you have something which lives without perturbation, then it is valid question. Let's put perturbation and see if it will live or not. But if something is dying anyway, and it is statistically considered, then yeah, can you clarify the meaning? Because basically what I am saying that despite instability, it will be always some perturbations for which it will live as before.
So, okay, I think I need to even clarify your question for myself. So you're saying they are occurring? I mean, you're losing them anyway. So I suppose what these results might be informative here is if there's too much perturbation injected at the beginning, they could affect the formation of these sort of peregrines.
I think mathematically everything is correct.
Yeah.
I was just trying to understand.
Yeah. I think that would be my statement on that one.
So I guess that my question is related to what Sergey was asking. So how does this instability affects the formation or the distribution of rogue waves in this equation? Have you thought about that?
Sure. So this is one model of a rogue wave, right? It's not just saying the rogue waves are the modulation space. So to me, this says the peregrine as a rogue wave model is susceptible to instability. I think it's relatively weak instability. So to me, it says it could affect the formation of peregrine solitons if there's enough perturbations in the formation conditions. They may affect how likely they are to occur in some sense.
I have a more general question. Usually when people show the images of rock waves, they look like isolated waves to me.
Yeah.
But in this theory, we are talking about the envelope of some carrier wave. Yeah. I don't think we see the evidence for a carrier wave in any of the pictures that we see. So how can we relate that to the images of rock waves?
It's So I mean, we have a carrier wave right here. We have we're modulating it. And so we're looking at the envelope here. And so I guess I'm trying to understand your question.
I mean, the images of the ocean, then you're showing.
Yeah, oh, yeah, okay. So, like these, right?
Like this, for example.
Yeah.
It's like just an isolated, like KDD type solution, right?
Yeah.
Rather than NLS type.
Well,
I kind of don't see the carry back, yeah? So
well, we're looking at the envelope.
Soliton or Kuznetsov is the envelope of a carrier.
Yeah, right.
I don't see carrier wave in any of these images.
Well, yeah, oh, yeah, sure. Oh, go forward here. Yeah.
How many oscillations do you have in the soliton? That's the question, I guess.
But I think the Peregrine breather is not really necessarily a model of the ocean. I think it's more used in the lab to create rogue waves because it doesn't have all the other oscillations.
That's exactly what I'm saying.
Yeah, but I mean, still, it's
not that kind of wave.
essentially, I think the instability, in some sense, proves that you may not observe it in the ocean.
Yeah, I agree with that.
Well, would you join me in thanking Justin for a fascinating talk? We have a break there for coffee, and we return at 4 o'clock for the distinguished lecture.